Okay, so let's get started. The last time we finished the expectation, there's one last thing about expectation is the conditional expectation. Right? So we defined the expectation of a random variable to be the integration of all the realizations x times the corresponding density. This is the density PDF of this random variable. Okay, at this particular realization x. Now integrate over all the realizations will give us the expectation of random variable x. And then similarly, we can introduce the conditional expectation. We can condition on any event A. And this is simply replacing the PDF by the corresponding conditional PDF. Okay. And we have defined this conditional PDF in the previous lectures. So once we know the conditional PDF, we can calculate the conditional expectation. Okay, this is a conditional expectation. And in today's lecture, we are going to talk about a very important concept called functions of random variables. Okay. We have we have seen similar problems on functions of random variables in the previous lectures, but here we are going to deal with these functions of random variables in a more systematic way. Okay. So basically, given a random variable x, which means it has a omega and the sigma algebra and the probability law. So we have an underlying probability space, and the x, the random variable, is a function that maps each outcome to a real number. Okay, so that's the setup. Now we want to look at y equals to g of x. Okay. Well, this g is a real valued function. Okay. Basically, this random variable x will give any realization of this random variable is a real number. This real number is fed into this function g, and this function g will output another real number. Okay, so the relation is that any outcome omega will give us x omega. Okay, it's a random variable evaluated at this outcome, and this is a real number. And this realization of the random variables is fed into y, into g. Okay, so we have g x omega. So, and this is defined to be the random variable y. Now, equivalently speaking, you can write it as, now the random variable y, the realization of this random variable at a particular outcome is basically the composition of g and x at this outcome omega. Okay. So it's x omega first gives the realization of x, and then this realization is further transformed by this function g. Okay, so composition of a function and a random variable. Now, the first thing that we need to care about is whether or not this y is a valid random variable. Okay. We need to make sure if x is a random variable, then we need to make sure this y is also a random variable. And this puts some restrictions on the function g. So in order for y to be a valid random variable, we need to satisfy some minimum conditions, requirements. Okay. The first requirement is that the domain of this function must include the range of the random variable. Okay. The range of the random variable is basically all the realizations. All the possible realizations of the random variable. The reason is very simple, because otherwise, if a certain realization of the random variable falls out of the domain of G, then we cannot write G of X. This is not allowed for that particular realization. So in this case, at least we need to make sure the domain of G, the input domain of G must include the output range of the random variable X. And the second one is also very intuitive. So we need to make sure this event belongs to the sigma algebra for every real number y. Okay. Otherwise, we cannot work with the probability space. Okay. And this event specifically, it means the set of all outcomes so that G of X omega is less than y. Okay. So this type of event must belongs to the sigma algebra of the original probability space. Yeah, but these are minimum requirements. Okay. Now, in all the settings, we will assume by default that this is also always a valid random variable. So this transformation G so always makes this a valid random variable. So now let's look at such functions of random variables. Now, the question is that if we know everything about the random variable X, which means, for example, we know the CDF function. Okay. Once we know the CDF function, we basically know everything about this random variable. Now, suppose we are given this information, how can we calculate, for example, the CDF of Y? Right, because CDF is the most fundamental characteristics of a random variable. So this is our first fundamental question. How do we calculate the CDF of a random variable that is a function of another random variable? Now, the way to do this is to basically follow the basic definition of CDF. Okay, this is the only way to compute the CDF. So we write out the definition, which is the probability of this event such that the random variable y is less than or equal to a small value y, a value of small y. Okay. And because y is equals to gx, so this is equivalent to the probability of this event such that g of x is less than y. And it really depends on the specific example of this function g. We need to basically solve this inequality for x. Okay. Once we solve this inequality for x, we can obtain an event that is in terms of, for example, this x less than or equals to something like this. Okay. But this step may be more complicated than more complicated than what we expect. So we will see some examples later. Right? But the intuition is that we solve for x. Okay, and then this can be characterized by the CDF function of the random variable x. Okay, so that's how we relate the CDF of y to the CDF of x. So in particular, in this step, once we solve for x, this may depend. The solution of this inequality may depend on the value of this threshold small y. Okay. So this is the basic approach that we always follow this approach, starting from the CDF of y and then solve for this x in this inequality. So let's consider some examples. So the basic example is a linear transformation. Okay. So the random variable y is a times x plus b. Well, a and b are some constants. Assume that a bigger than 0. So this is called linear transformation. So again, we start from the CDF of y. Now, y equals to ax plus b. All right, so we have this inequality on x. And now this is a very simple linear inequality. So we can solve for x. It's very easy. So it's x is less than or equal to y minus b over a. Whereas a is positive, so dividing by a does not change the sign of this inequality. And this is probability of x, the random variable x less than or equal to a certain number. Okay, it's y minus b over a. So this is exactly the CDF of x. evaluated at y minus b over a. Okay, so this is the CDF of y in terms of CDF of x. So in this case, this is clear because solving this linear inequality is very simple. Okay. Now, on the other hand, if a is negative, suppose a is negative, then when we solve this inequality, this becomes greater than or equal to, because a is negative, dividing by a negative number will change the order of this inequality. And then if this is greater than or equal to, then this becomes 1 minus this CDF of x. Okay. So you can see it critically depends on this transformation. Okay, so this is a linear example. So let's consider a nonlinear example. Y equals to x squared. We start from the CDF of y. Okay, now we end up with this inequality, the probability such that x squared, this is a random variable, okay. X squared less than equal to y. This is the event of interest. Now we need to solve for this inequality. And this is a quadratic inequality. So you can, if you are familiar with quadratic equations, you can easily solve this inequality. But in general, you can draw a picture of x squared. Okay, so this is the quadratic function of y equals to x squared. So I should use capital letters. So this is a realization of random variable. This is y equals to x squared. Okay, the square of the realization of the random variable x. So we are looking at x squared less than or equal to y. So we draw a horizontal line that represents the threshold y. And if x squared, this curve less than or equal to y, meaning that the curve, we are looking at the part of the curve that is below this horizontal line. Okay, so it is this one, this part. So this gives us the interval over the x-axis. So this becomes the probability of x less than or equal to square root of y greater than negative square root of y. Okay. If y is bigger than or equal to 0. Okay. If this horizontal line is above 0, they have this intersection. Okay. So you can have this solution. But if y is below the x-axis, then there's no intersection between the horizontal line and this curve. So in that case, it is empty set. Okay, this event is empty in that case, which means x squared can never take a negative value. Okay, that makes sense because we are looking at x squared. Okay, so this case is easy. This is 0 by the probability law. So we just need to look at this one. And this is an event on X, so we can represent it using the CDF of X. So you can check the CDF properties. So it's the CDF of the right endpoint, this point, subtract the CDF of that left one. Okay, and plus because this is greater than or equal to, so so basically, if you write this out, be more specific. This is the probability of X less than or equal to this one. Subtract 1 minus subtract probability of X greater than negative square root of Y. Right, so if we draw a picture, right, so it's a probability of X less than or equal to square root of Y. Subtracted this part. I think it should be less than 1. Subtract this part. But this is the CDF of Y, CDF of X at negative square root of Y, subtracting this probability density, probability mass at negative square root of Y. Okay, because this is less than, strictly less than. Okay, well, the CDF is less than or equal to, so we must add this probability mass back to the this CDF. Yeah, so this is less than equal to. Well, this is less than, or this is strictly less than. Well, here we have less than or equal to. So these two are different. This is the CDF. Okay, so have to be careful when you write out this CDF functions. So this is when when Y is bigger than or equal to 0. Right. So you can get a sense of how to derive this, how to solve this inequality, especially when this transformation is nonlinear. Okay, you start from you can sketch these functions. So x squared is this quadratic curve, and then you start from a horizontal. You draw a horizontal line which represents the value of y. Now you move this y from top to the bottom, okay, from positive infinity to negative infinity, and see what are the intersection points between this. So you are looking for all the regions, all the values of x on the x-axis, so that this curve is below this horizontal line. Okay. And those values of x forms the solution of this inequality. And then you need to vary the position of this horizontal line. So sometimes the values of x may change depending on the position of one. In this case, we have a change point, which is y equals to 0. If y is bigger than or equal to 0, we have a non-empty intersection, and then we have this solution. Otherwise, if y is below 0, then there's no intersection between these two curves. So the resulting event is empty event. Okay, we can consider a slightly more complicated example. X is a uniform random variable between 0 and 1, and y, let's consider the transformation y equals to the square root of the realization of this random variable. Okay. So we have, so because x is uniform, so we know the PDF and the CDF. When we say uniform, this implies that the PDF of this random variable is 1. And between 0 and 1, okay, and 0 otherwise. And with this PDF, we can take integration and get the CDF. So I will skip this part. So integrating a constant function over an interval gives us a linear function. Okay, so this is between between 0 and 1, we have a linear function. As bigger than 1, it achieves the maximum value 1 and keeps constant afterwards. Okay. And then we start to look at the PDF of y, which is probability of square root of x less than y. Okay. Because now the random variable is square root of x. Now, when we look at this, again, we can sketch functions. The square root of x looks like this. Okay, it starts from 0 and grows with regard to the square root of function. But we can see that this function is not, the domain of this function is only on the positive domain, okay? Because we have a square root, so x can only take positive values. In this case, x is a uniform random variable, so it's guaranteed to be between 0 and 1. So there's no issue about taking the square root. Yeah. However, this y can be arbitrary. Okay? This y can start from positive infinity to negative infinity. So if we draw a horizontal line of y, we can see that if y is positive, then we have these two curves will have an intersection. Okay? However, if y is negative, then there's no intersection. And the other thing is that this random variable is restricted to be 0 and 1. So actually, I need to. Okay. So this is all the values that this random variable can take between 0 and 1. So this also restricts the range of this square root of x. So here we have 1, because the square root of 1 is 1. So we have two change points here, depending on the position of this horizontal line. One is 1, the other is 0. Okay. If y is above 1, then the entire curve is below y. So it is guaranteed that square root of x is less than y. Okay. Now, if y is in between, we have an intersection, and we can solve for this equation. We can solve this equation for x. If y is below, there's no intersection. So we have three cases. The first case is y is bigger than or equal to 1. Right. It is if y is greater than or equal to 1, then everything no matter what values of x we take, it is square root of x is always less than 1. Because x is between 0 and 1. So this basically means x between 1 and 0, which is 1. This is all the values of x can take. If y is between 1 and 0, then we have an intersection between 1 and 0. So we have an intersection. And if this is y, and this should be y squared. So this is the probability of x less than equal to y squared, greater than 0, greater than equal to 0, which is the CDF of x evaluated at y squared. This lower bound is guaranteed because x is a uniform random variable. So you just need to care about this part. And then if you look at this CDF function that we just derived, fx at x is simply x. So this is actually y squared. Okay. And the last case is when y is less than equal to 0. We have 0. Yeah. So if you sketch this CDF of y, if y is negative, CDF is 0, and then we have a quadratic. It grows quadratically up to 1. After that, we reach the top of this CDF function. So this is CDF function. Okay. So the idea is that you first sketch this function, and then you start from you draw a horizontal line. Okay, start from the positive infinity, move it to the negative infinity. See what are the intersection points. Okay, those intersection points defines the solution of this inequality, and then you can, once you solve this inequality, everything should be clear. But when you sketch this function, make sure you understand the limit the domain of this function. Okay, in this case, x is between 0 and 1. Because x is a uniform random variable. So when you sketch this square root function, it should be between 0 and 1 only. Okay. So there's one last example I want to go through. So we define the random variable y to be a piecewise linear function. Okay, so this is the transformation. And you can first sketch this this function. So we have two change points, C and negative C. Now in between we have 0. If x is bigger than C, this is a linear function. So otherwise, if x is less than equal to negative C, we also have a linear function. So in this case, this is the continuous point, and this is the discontinuous point. Right? So these 2 points are different based on how this function is defined. And then again, you start from a horizontal line at infinity at the very top. So you can identify so in this case, we want to look at probability of y equals less than equal to y. Okay. And really depends on the value of this small y, we have different solutions. Now, clearly, these discontinuous points are the so-called change points. Okay? So we need to be very careful. Now, this is the one change point. So we need to look at the case where the y is above this change point. So this is C. Okay. Now, if y is above C, y is above this point, then this inequality corresponds to, now we can solve this inequality. This is y, and we have this is also y. So x, any x less than or equal to y will make y less than or equal to this small y. Okay, so this is the change point. So this is f x at y. And this is when y is above this change point. Now, when y achieves C, when y is here, you can see that this function, we need to look at the part of this function that is below this horizontal line. In this case, this part, this horizontal part plus this linear part, they are below this horizontal line. And in fact, because there's a large gap between in this discontinuity point, at this discontinuity point, so if this horizontal line is in between these 2 points, okay, the solution is always the same. It's always this part plus this part. So this is when y is less than equal to c, but is bigger than equal to 0. Right? When the horizontal line is in between, the solution is always fixed. It's always x less than equal to c. Right? This part plus this part. So x is less than equal to c. Right? So this is when y is between c and 0. Okay. And then we need to look at, we further move this y lower than 0. And here we have another discontinuity point. So if y is lower than 0, but is bigger than equal to negative c, because here is negative c. Okay. If y is in between these 2 points, if you draw a horizontal line here, if y is here, then the part of this function that is below this horizontal line is only this linear part. So in this case, x is less than equal to negative c. Okay, only this part is below this horizontal line. Now, lastly, when y is less than negative c, meaning that this line starts to intersect with this part, this linear part. This means x should be less than y. Because the intersection point again is y. This is the curve y equals to x, right? So in this case, y less than equal to small y is equivalent to x less than equal to small y. Okay, we need to look at this part, basically. And this gives fxy. Right. So we have 1, 2, 3, 4, 4 different segments. Okay, for the CDF function of y. Okay. So when you do this, you will need to move this horizontal line little by little and see where are the change points. Especially when this function has a lot of discontinuities, those discontinuities will cause very different solutions for that inequality. Okay, so this is the one of the approaches to calculate the CDF of y. Okay, well, when y is a function of another random variable. Now, once we have this CDF function of y, we can always calculate the PDF of y by taking the derivative. So next, let's talk about how to compute the PDF of y. We need to compute this one in terms of PDF of x. There are two different approaches. One is calculate the CDF of y first. And then from there, we get the PDF of y. Right. And to calculate the CDF of y, we follow the previous approach that we explained here. Okay. We just start from solve that inequality and look for the change points. And we can identify the PDF of y as CDF of y. Once this is done, we can further compute the PDF function. Okay. But this is a kind of a complicated approach because we need to go through the CDF first and then get to the PDF. Now, the second approach is to directly relate the PDF, directly compute the PDF of y from the PDF of x. Okay. If this is given, and the way we compute these PDF functions is through the following fundamental theorem. The fundamental theorem says that gives us a formula to calculate the PDF of y in terms of PDF of x. So the theorem is as follows. So let's look at a given threshold y, which is a real number. And then we need to solve this equation. For any y, we solve this equation for these roots. Okay, let x1, x2 denote the roots of this equation. We could have many of these roots depending on the function of g. So basically, you solve this equation for x, okay? And we will have many different roots. We denote those roots as x1, x2. Once we have these roots, the PDF of y is given by is the PDF of x and these roots divided by the derivative of this transformation function and these roots. Right, the absolute value of the derivative, and we sum over all the roots. Right. So you get all these roots, x1, x2, up to xk. Now for each root xk, you compute this ratio, which is the ratio between the PDF of x at this root over the absolute value of the derivative of this transformation function at this root. You sum up all this ratio over all the roots. So this gives the PDF of y in terms of the PDF of x. So we can see that this formula depends on how many roots we have associated with this equation. So there's a very simple explanation on the lecture note that shows why this formula makes sense. Okay, here I can briefly go over this argument. So the PDF of y, by definition, is we are looking at the probability of this event over delta y. It's the density of this random variable at y. So we basically consider a small event defined around a perturbation at this point y. This is a small event. So the probability of this perturbed event over this perturbation delta y. Okay, this is the definition of this density, the concept of density. So you consider this perturbed event around this y and divide it by the perturbation delta y. So therefore, we can approximately say that the PDF multiplied by delta y, well, delta y is a small perturbation. Okay, is approximately the probability of this perturbation event. And then we can generally look at this event. Now suppose this is x and this is y equals to gx. This is a function, very complicated function, could be. So we need to look at this event. We solve this inequality, right? So this event is defined by the intersection of two horizontal lines. One is y, one is y plus delta y. Okay. Now we look for all the x so that this g of x is in between these two horizontal lines. Okay. Now if you look carefully, we have many different intervals that gives this value, that satisfies this inequality. This is one, and we have this one. Right. And in fact, these locations are the corresponding solutions. For example, this point is the intersection between y and this curve. So this is one of the roots. Okay. And this is the corresponding perturb. A perturbation. So basically, intuitively, these different intervals, they are located at the roots, around the roots of this equation. Okay, so it depends on how many roots do we have at this specific location y. So specify a value of y. We may have different number of roots, okay, depending on the value of y. So in this case, we have 3 roots for this specific function. Okay, so this event is equivalent to probability of x within these intervals. Right, this is the first interval. So again, we are solving, right, like in the previous CDF approach, we are solving this equation for x. So now we have 3 different intervals. Okay, and so on. And then this is a perturbation event, probability of a perturbation event on x. So similarly, we can argue that this can be approximated by the PDF of x at these roots, because this is a very small perturbation, right? So at x1 multiplied by the length of this perturbation. Okay. Depending on the function, sometimes the perturbation may be positive, sometimes may be negative. And similarly for all the other roots, we have the same formula. And this is a density of x at this root. Now, this perturbation on x can be regarded as perturbation of y over the derivative of g of x at this root by the chain rule of derivative, right? Because this is, think about that, this is delta y over delta x. Right. So by the chain rule, this gets canceled. So you have delta x back, delta x1 back into this absolute value. Okay. So in the end, this delta y can be canceled because we start from fy times delta y. If you cancel this delta y, assuming the delta y is very, very small, right? So you end up with fx at the root divided by the derivative at the root, and then sum over all the roots. So this is how we intuitively, how this is the, this gives the formula for this PDF function. Okay. So it depends on the roots of this transformation function. So we can directly apply this formula to calculate the PDF. Yeah. So let's consider one example. There's another, I will skip the linear example on the lecture notes. You can take a look by yourself. It's very simple. It's just a direct application of this formula. Now, the second example is that the resistance of a resistor, let's assume it is a uniform distribution between 0.9 and 1.1. It's a random variable between small interval. And we apply a constant voltage okay, we apply a constant voltage to the resistor. This is 1 volt. Apply this constant voltage to the resistor. Let's find the PDF of the current. Okay. So we know that the current I is the voltage divided by the resistance. Okay. Now this voltage is a constant 1, so it's 1 over the resistance. But in this case, the resistance is a random variable, okay, due to manufacturing variations. So in this case, the current is 1 over this random variable R, and this is a function of random variable. Okay. So we know R, we are given the PDF of R, which is a uniform PDF over 0.9 and 1.1. So we have the PDF of R, we have this function, so we can apply the fundamental theorem to calculate the PDF of this current. So to do that, first of all, we know that this gives the PDF of resistance we can calculate that the PDF between 0.9 and 1.1 is 5. Okay, this is the PDF of the random variable R. Now, to apply the fundamental theorem, we need to look at the root of this function. Okay. So if the resistance is between 0.9 and 1.1, we know that the I the range for the current should be 1 over 1.1, 1 over 0.9. Right? Depending on the variation of the resistance, the variation of the current is bounded by this interval. So basically, if we consider the current within this interval, then this equation has one root. And the root is R equals to 1 over Y, or 1 over I. And so this is the only root for this equation. So Fi by the fundamental theorem, because we only have one root, right? So it's Fr at this root over the derivative of the transformation at this root. So we write down the original formula first. Now let's look at how to calculate each term. Okay, so the numerator is plugging in Fr, but R1 is 1 over I, so I plug it in. Now for the numerator, we need to calculate the derivative at R1. Well, this function this is a derivative of g, right? Taking derivative of this function, we have -1 over r squared evaluated at r1, right? And take absolute values. So this is gonna be okay, this is gonna be negative I squared. Right. R1 equals to 1 over I. So you plug it in to this formula. You have 1 over I squared. And then this is 1 over this R squared. So you have negative I squared in the end. And within this interval, the density, okay, 1 over I is between 0.9 and 1.1. So the density of the resistance is a constant 5. So it's 5 over I squared. For I belongs to this interval. Otherwise, it is 0. Because otherwise there's no density of the resistance. So it is basically 0. Right, so this is so you basically you first identify if we know the PDF of this or of the original random variable, then we can consider applying the fundamental theorem. So the challenge here is to solve for the roots of this equation. And the roots really depend on, you need to consider the range of the original random variable. And then for different values of this random variable, we may have different roots. Depending on the value of I, we may have different roots. Okay. So this is the transformation of functions of random variables, right? We have two different approaches to identify the CDF and the PDF. One is to directly look at the CDF function. And then for this one, we need to carefully look at the variable of this CDF function. This is to directly compute the CDF function, but sometimes we care more about PDF functions. So in this case, we can apply the fundamental theorem to calculate the PDF function. And to use that, we need to solve the roots of this equation. And based on the number of roots, the PDF of y is given as follows. Okay. When you solve this equation, you need to look at, in some cases, depending on the value of y, the equation may have different number of roots. Okay. For example, if you look at y equals to x squared, now if y equals to 0, we only have one root, x equal to 0, right? If y is bigger than 0, then we have two roots, which is positive or negative square root of y. Okay. If y is less than 0, we have no root, right? So these are different cases depending on the value of y. Okay. So this is how we calculate the CDF and PDF of functions of random variables. And then, so once we using these approaches, right, we can get all the basic information of the random variable y. So we can get the PDF of y. So we can also define for these functions of random variables, we can also define all the statistics like expectation and variance. Okay. So in particular, the expectation of y is given by integration g of x is simply integrating. If we know the PDF of x, right? So calculating the mean of y is very simple. It's integrating gx multiplied by corresponding density of x. Because this gives the realization of y, whereas this is the corresponding probability density. So y is realized by x. So it's corresponding realization multiplied by density. Or equivalently, if you calculate the PDF of y through the fundamental theorem, then you can use a very basic definition of expectation. Right? If you calculate this first, then you can take this integration. This is a basic definition of arbitrary random variable y. But in this case, sometimes it is easier to work with this one because we already know the PDF of x, and gx is also given as an explicit function. Okay. Now, for example, we can consider this function y equals to gx. Consider this random variable. Well, this g is defined as follows. Okay. This is a transformation. And this function g is basically subtracting the mean from this random variable and then taking the square. And this is a valid quadratic function because in general, given this random variable x, expectation of x is a fixed constant. This is a constant. We can calculate the value. So this is a certain constant. So it's basically x minus a certain constant to the power of 2. So it's a very standard quadratic function. We just treat this as a constant. And in this case, expectation of y, the expectation of this random variable is basically the expectation of this quadratic. Okay, so the expectation of this one, which is actually the variance of the random variable x. Now, but before we define the variance of a random variable to be this one. Right. Now think about that. First of all, this gives a transformation of x. So this defines a function of this random variable x. And such a function of random variable x defines another random variable y, right? Since y is a random variable, we can take the expectation, right? And in the end, the expectation of y, which takes this form, is actually the so-called variance of a random variable x. So it measures so here inside is the deviation of the random variable from its mean. Okay. And we take power of 2 to measure this is a measure of deviation. Now we take the expected value of such deviation. Okay. This gives the definition of variance of a random variable. Now, in particular, we can further look at this. This is a very interesting statistics of a random variable. So the variance of x, which is, we also call it, we also denote it as sigma x to the power 2, which is so the standard deviation is defined as the square root of the variance. Okay, so the variance is the square of the standard deviation. So this is just the notation and definition. But anyway, this variance is defined to be the expectation of this deviation. Now, this is a quadratic term inside, so we can expand it. So we have x squared minus 2x times ex plus ex to the power of 2. Right? You must be very, very careful. Okay, this is a constant. So it's x squared, and the cross term is negative 2x times this constant. And the other term is this constant to the power of 2. So it's ex to the power of 2. Okay, now let's look at these terms one by one. The first term is x to the power of 2. This is a random variable. It's a function of the random variable x. So again, this is a random variable. So we can take the expectation of this random variable. Now we have, when we discuss the expectations, we have showed that expectation is linear, right? So the inside is a summation of 3 terms. So we can calculate their expectation one by one and then add them up. So this expectation is a linear operator. So it is the expectation of the first term. Now what about the second term? The second term, we must be very careful. This is a constant, and this is also a constant, right? It's this constant times the random variable x, taking the expectation. By linearity of expectation, we can take these constants out first, and then taking the expectation. Right. So these 2 ex, they are constants. We can take them out. Now, what is left is this random variable x. So we further take expectation of this random variable. That gives this another expectation term. Now the last term is a constant. Constant is not any constant taking expectation is the constant itself. This is a constant. So in the end, these two, this gives 2ex to the power of 2. Okay. So this term can be canceled with this term. So we have ex squared minus ex squared. Okay. So the variance of a random variable is actually can be calculated as follows. So it's the expectation of the random variable x to the power of 2 minus the mean to the power of 2. Okay, so this is the very fundamental equation for the variance that relates the variance to the expectation. Okay. So in the next class, we will talk about started to talk about these higher moments. We call this the moment of these random variables. And so the variance is kind of a second moment of the random variables. And this is a very important characteristics for random variables. Okay, so when we deal with expectation, make sure you understand that these here, the expectation are constants. Okay, they are constants, so you can treat them as some real numbers, whatever. So the only random variable, randomness here is these two. These two x, they are random variables. Okay, you can go over this offline, following the lecture notes. Okay. So I will have office hours this afternoon, starting from 1 to 3. And feel free to join the Zoom meeting.